All right, so let's get started. You guys hear me, right? Is anybody missing? Derek, right? All right. So I brought some crystal structures for you guys to play with. So a quick review of what we have done. We have lattices, right? And lattices with bases. We also know how to make the simplest lattice by convention, right? If we have a lattice that is maybe something like this, right? Then we take, for this point, we start taking the halfway between each of its neighbors. So the halfway between these two is this one. 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 And then the halfway between this one and this one is going through here. And you see, this is the first Brillouin zone. Sorry, that's the Wigner side cell. Wigner side cell. That's how to build the simplest lattice. And if you have a cubic one, you'll see that a cubic distribution of the lattice points, you'll see that you'll get a cube. So now, it's hard to tell how things behave in 2 dimensions when you're talking about 3-dimensional objects. So I brought a couple of things right here to play with today and look at them, and you can grab them. If you don't feel comfortable touching things, it's okay, you don't have to touch them. But they're here, and there's a few different ones. So this one, if you assume that all of them are the same atoms, disregard the coloring, this would be the cubic cell, right? And if you start thinking like, okay, now there's going to be a difference, you can take this atom to be different from the red ones. Then you can see that the cubic cell goes from here to here to here, like this, and like this. So it becomes this cube that is made with all of those atoms. And further, if you do that, you can assume that some of them are not there, right? So assume that the red ones are not there, and you have this same cube, which is made from here to here, here to here, here to here, like this. As the cube, the red ones are not there, and now you have the face center cubic. So that's why I brought this one. If you wanted to do the body center, then disregard, make again the same 4 atoms like this, and disregard everybody except that is not a corner except for this red one in the center. That's your body center cubic. And if you start looking at those in 3 dimensions and able to move them, you get a better idea. So we have the square lattice here. We have that we can make something with the bases, right? So this is just the square lattice. So I brought this paper right here to show you the honeycomb lattice. This one right here. All right, so this one is, if you assume that the 2 A and B are the same, this is the 2-dimensional structure for graphene. So this is a lattice with a basis. It has a basis because it's not in this unit cell. The unit cell goes from here to here. So the unit cell goes from here to here, from here to here. So we have to translate this vector over here. So that means that our unit cell is going to have that vector translated there. And then this A1 vector translated here. So this right here is the unit cell. It's then easy to see that it has B atoms right here. All of B atom is inside of it. And then it has a little chunk of this A atom, a bigger chunk of this A atom, a bigger chunk of the A atom over there, and then a big chunk of this atom A over here. So if you took all of those A pieces of those atoms, you make another atom A. So that means that this lattice for graphite, this honeycomb lattice, the A1 and A2 are the primitive vectors. That's a unit cell that you can make for this. It's not this unit cell is not the simplest unit cell, right? Because we just drew it from those two vectors. You can have a Wigner size cell for this guy, which I haven't drawn here. But we see that it's not just the points on the corner of the unit cell that we just have, but also this atom B that is inside of it. So this B becomes the basis. So we can think of these lighter A atoms as the corners, at the corners of my unit cell. Those are the points of the lattices. Just like these ones are just the points in the lattice, right? Over here. So at this point, these are points in the lattice. And what we added is that now we added that there's a B atom here inside of this lattice. So if I have this as my cell, right, I could actually make something like this. This is my unit cell now. And I put those 4 atoms in it. These are the points on my lattice, this one right here. Remember, it's 1 point in the lattice. But then these guys, these 4 black dots, are my bases. So they're decorations that I add along with the bases. So mathematically, the lattice points are these blue ones. My unit cell doesn't have to be centered on those blue lines. But if I drew the Wigner size cell, then the lattice is centered so that my unit cell has one of those atoms in the center. If I make that way to make it. All right, questions about this? So these are just definitions, but I want to make sure that you guys have the definitions down. So these decorations are my lattice. Sorry, my bases. All right. Another thing important here is how do we find the basis? In this case, I have the A1 vector here, the A2 vector here, that defines my lattice. And then this tau vector defines the position of the basis. So A, this first A, is located at 0, 0, right? Assume that this is the 0, 0 position. And next to every A, a distance tau in the direction of the vector tau is going to be each of your B atoms. And that's how you build the lattice with the basis. That's your basis. Does it make sense? Yeah? All right. So here's another picture. And this is the diamond lattice. Okay? So this is the diamond lattice, because this is what diamond, if all of the atoms were carbon, this is the unit cell of diamond. This is one of the unit cells, not the simplest unit cell. And what it is that it is two FCCs, phase center cubics, intersecting each other. And then if you make one of these atoms different from the dark ones and the light ones being different, like for instance, this is called the zinc blende lattice when they're different from each other. And it's one of the most popular lattices that you see in semiconductor compounds and systems. So for instance, gallium and arsenide, they make the zinc blende lattice. Indium and arsenide, antimony and tin, a bunch of those guys make compounds, make that zinc blende lattice, where one atom would be taking this place, the dark ones, and the other one, the light ones. So it's a really important, lattice in terms of solid state physics. Sorry? Yeah, so we have the diamond lattice. And then the other one is called the zinc blende lattice. So the main difference is that the zinc blende lattice is the two atoms are different in your lattice. And the diamond lattice, they're the same type of atom in your unit cell. So crystals that you normally see in nature can be the zinc blende lattice, a lot of them. So if we look at let me bring this up again. This guy right here. So this is our zinc blende or diamond lattice, right? And what we have is that the Brat-based lattice that the zinc blende takes into is the FCC lattice. Why is it the FCC? It's phase center cubic, because you see that these light atoms are at all of the corners, right? And then there's this atom right here at the face. This one is at the face, this one is at the face, this is in the front face, this is in the back face, this is on that direction face. So the light atoms, the light dots are the FCC lattice. And then what we see is that this is the basis, right? And it's 1/4 of the way along the diagonal right here. So there's a diagonal that connects this point to this point. And this is 1/4 of the way across. So if you take this atom and move it 1/4 of the way, you get this diamond lattice. And they're identical. If you shifted this thing in that direction, you would see that now the black dots are the ones that make the FCC lattice, and the light ones are displaced 1/4 of the way in the diagonal. So they're identical. Questions? No? All right. So one of the things that we talked about is how many neighbors each of them has, right? So if we look at this particular one, we could talk about how many neighbors he has. Like this guy, if it's neighbors with the gold one, right? Back here. In the cubic cell, we're assuming that this is a cubic cell. So this gold one has 1, 2, 3, 4, 5, 6 Nerex neighbors. Now, if we look at the FCC, it has more neighbors. The body center cubic, it has more neighbors. And we looked at how compounds like to have neighbors so that they can match their chemistry, how many valence electrons they have. So for instance, carbon has valence 4. It likes to make the diamond lattice because in the diamond lattice, each of the carbons is going to have 4 neighbors. Does that make sense? So that's why it makes the diamond lattice. And each of the atoms in the carbon is using its electron to make a bond with its 4 nearest neighbors. So all of the electrons in the diamond lattice for carbon are making bonds. They're all valence electrons. So what does that mean? Carbon is a really bad conductor because all of its electrons are being used to make bonds. So diamond is a really bad conductor. So now let's go back to this guy, right? Here's our diamond, not the diamond lattice, but the graphite lattice. How many at the graphene or graphite, how many atoms is this guy connected to? 3. So graphite is this type of a structure, and there's one on top of the other. And they don't line up exactly like my fingers where they line up on top of each other, but they're displaced a little bit. So there's sort of like a built-in offset. Yeah, so you have one here, one here, one here, one here. So they go like this. So if you look at them, this guy is connected to 3, this guy is connected to 3. That means that for graphite and graphene, each of the carbons is making 3 bonds, and it has an extra electron to move around and conduct electricity. So that last electron is free. So that makes graphene, which is this 2-dimensional thing that exists, a really good conductor. Yeah?
Actually, now that I think about it, is the reason why it layers with that offset due to the pressure between the electron shells of the different lattice structures?
So each of these guys, the next one on top of it is just displaced by a bit. So there's an A atom right here. There's going to be an A atom right here. And they just like to be like that because that's the lowest energy of formation. Right. If you put them on top of each other, there's repulsion, electrostatic repulsion. So think about it this way. This guy is connected here to 3 of them. And then it has electrons that are able to free to move. And then you have another one here that is doing the same. And the way that they talk to each other is not by making, the way that they interact this layer with this layer is not through electrons moving back and forth, but rather through van der Waals interactions. So how many of you know van der Waals interactions? Have you heard of it? Who can tell me what it is? Monsieur? You know what it is? Uh-huh. But do you know what it is? What a van der Waals interaction means? So yeah, it's using the ideal gas. It's one of the approximations that we use. But do you know why or what it means? All right. So van der Waals interactions is interactions between, if you're thinking ideal gas, we could think of having a sphere right here and another sphere right here. And then there's a distance between them. So now, this distance r, you can tell if this were positive and negatively charged, they would interact through a Coulomb interaction, right? Or plus plus. Sorry? Cohesive force? Yeah, the cohesive force. So basically, if this is neutral, right? And this is neutral, do they interact with each other? So you know if they're plus and minus, or plus and plus, or minus minus, they would interact through each other through Coulomb. In this case, this is a neutral body, this is a neutral body, but actually they do make themselves attract to each other and repel each other. So the potential that you use is actually gonna look like this. So there's a little hump right here, and then it goes to 0. So this would be the potential as a function of distance. So that means that they like to be separated from each other and around this equilibrium point. This is the minimum of the potential energy. If you push them close together, they're solids, right? So they don't like to get on top of each other. And if they move apart from that, they actually attract each other because they don't like to be far away from each other. So in this region, they're repelling each other. They don't want to be on top of each other. In this region, they attract each other, and then the potential just goes to 0. And the first one to come up with a model of this interaction was van der Waals. And that's how neutral systems would interact with each other. So for the graphite layers, they have a particular distance that they like to be apart from each other. And the interaction potential is attractive there, but it's not too strong. It's kind of weak. So it's not like a covalent bond or an ionic bond that is hard to break. This is really easy to break because it's a shallow interaction right here. Like if this was Coulomb interaction, it would go down like that crazy, all the way down. So for those two particles, that's the kind of potential that they have, van der Waals forces. They're really weak. So you can break apart graphene out of the graphite by just using a Scotch tape. So that's one of the different bonding that can happen between layers. So the Lennard-Jones liquid is similar to this. That potential is similar. The van der Waals interaction, yeah. So the Lennard-Jones is the name of one of the potentials, and that's the van der Waals interactions that you would see. Yep. Yep. All right. So, So we talked about the diamond lattice. We talked about how graphene, it has 3 instead of 4 valence electrons. So that's the reason that graphene is metallic, because it has electrons to share to conduct electricity. Every atom, carbon atom, is donating one of its electrons to the lattice and letting it run crazy all over the lattice. So that makes it a metal. Versus diamond, that keeps carbon in diamond structure, keeps all 4 of its electrons attached to the other carbons, and they're creating that bond between them. So sodium chloride is a cubic structure. You will have a positive, negative, opposite charges. Sodium is positive, chlorine is negative, and they form the cubic structure, and that's the one that they like to form. All right, so the next thing I wanted to talk about is symmetries. So let's talk about rotation symmetry. So this is a molecule, right? Assume that this is carbon, assume that this is carbon, and that these are hydrogens. If I have this one right here, I have methane. It's a carbon with 3 hydrogens, right? So there we go. This is what methane might look like. Actually, not exactly, because this bond right here is longer than the other ones. But let's assume it is. And you have this symmetry of it. For instance, if I grab it here, methane, right? I could do a rotation. So if I go along this axis, so this is my axis of the system, the one going up through here, right? If I do a rotation of 60 degrees, so hold on, if I do a rotation of 90 degrees, I would be coming back to this. So that's not a symmetry because it's not the same by 90 degrees, right? Is that clear? 90 degrees takes me here. But if I do one with 120 degrees, I go back to that. So a rotation along an axis by 2 pi over n, n being an integer, right? That takes you back to itself, that's a symmetry of the system. So here, if I go in this direction by 120, I get the same molecule. So this has 2 pi divided by how much? 3, right? 120 is 360 divided by 3. 2 pi is 360. So that would be one of the symmetries of the system. All right, so let's look at this molecule right here. Now I'm attaching two carbons together. What's this one? Two metals together, basically. Cosmo? Has a name. Hank Hill, anybody? Do you guys know Hank Hill? He will be really proud of you if you knew which molecule this is. Casper? You don't know Family Guy? No, wait. King of the Hill?
No. Oh,
Propane. Are you that young that you don't watch King of the Hill? How about you?
I mean, yeah, I never watched it either.
All right. So this one has two, let me make it symmetric right here. Two carbons, and each of them is attached to 3 hydrogens. So if I have them symmetric like this, then they would have the same symmetry, where if I rotate from here to, wait, it's not rotating together. Like this, it gives me back to itself. So this needs a rotation of 120, right? To get back to itself. But now let's say that I twist these guys, and instead of being like that, they're now like this. So it's hard to see, you have to touch it, but you can tell this one is down, this one is up. This one is down, this one is up. So this would be the two in this plane of the carbons. So now, if we look at it, you guys can tell the symmetry of this one. So now this system, this guy is at the bottom, and this guy is on the top, and this guy is on the top. So these two have to be the same. So there we go, kind of like that, right? So now here, if I rotate by 120, do I go back to itself? So let me do that again. So it has the same symmetry, right? So it has the same operation, which is rotation by 120 degrees, gets me back to itself. So that's a big symmetry of the system. This one also has it along this axis. Other things that I can do, if I have a square lattice, this one right here, I can rotate it by 90 degrees. So 90 degrees brings me back to myself. So this is my lattice. And then if I do only 45 degrees, you see that it's not the same. But if I do 90 degrees, it's back to itself. So this has fourfold symmetry. N tells you the number So we have n-fold symmetry. All right, so you could change the axis on it. For instance, let's say that I wanted to do, so right now I was doing it through this axis, through it right here, right? That's my axis. What if I wanted my axis to be from this corner to this corner? Let's say I had an axis that is going through the corners. Then I could tell if I rotate it along that axis, how much angle do I need so that it goes back to itself? Does that make sense? You can tell what n-fold symmetry has along this axis. So it's easier if you play with it, you grab it with your hands and you start rotating it like that. So it depends on what axis you're going through. Another symmetry that we can have is reflection. So the reflection is usually through a plane. So let me put this here. Again, this is the symmetric one where the two up right here. So if we look at it from the top, there's a plane. This plane right here is my symmetry plane. Do you guys see it? So if I cut it through here, it's the same on this end as this end. If I have it here, so I rotated it, there's also this plane that is symmetric through reflection. Does that make sense? So I can cut it through here. If I cut it through here, you would see that it's identical. So we have this plane here. We have this plane through here. If I cut it through this plane, is it symmetric? Exactly. So we had reflection about a plane. So a plane is in 3D or a line if you're in 2 dimensions. So you're looking like, is there a mirror line in this system? Okay, that makes sense? That's an easy one, right? All right, so then now let me go to a hard one. Inversion symmetry. So inversion about a spatial point in the lattice. In 3 dimensions, right? If I take this guy, the question is there a point around any point in this system that I can rotate it by 180 degrees and get back to itself? So for instance, if I pick this point, right? This is an inversion point right here, because if I rotate by 180 along that line, around that point, so let's put my axis here on this point, and then I rotate by 180 degrees, do I get the same thing? Does that make sense? So that's an inversion symmetry along this point. So now let's go back to this one. So this one is different, right? This one like this. So if I grab this two, you see that those 2 atoms are in that same plane. Yeah? Cosmo?
No.
All right. So these 2 atoms right here are in the same plane right here, right? But one is in this up and one is in this up. So if I have this point and I do the rotation by 180, does it bring me back to the same point? Yes, right? So that's an inversion symmetry of the system. So this is an inversion symmetry that I can go through this point right here. So it doesn't matter if they're both like this, where the two are up, or if I rotate it so that there's an up and a down. This is the actual molecules configuration, not the same up and up, but up and down. But there's still that rotation symmetry that I have, this inversion point through here. And there's different inversion points, right? Like if I'm looking at from the top, I could say that this is an inversion point. Well, let's see if this is an inversion point right here. If I have this one right here as my inversion point, and I do a 180 rotation, is it the same? No, right? So then this is not an inversion point, a rotation along this plane. If I have it like this, right? And then I do, let's say that I want to see if this is an inversion point. I take this point right here and do 180. I get that. So that's not an inversion point, right? But now, what if I reflect it, right? And my reflection is, sorry. And then I have another rotation down here, and then I bring it like this, and that brings me back to the same point. So now I did two symmetry operations. First is a rotation by 180 in one axis, and then another rotation by 180 in the other axis, and I went back to the same. So having two operations done at the same time is also another symmetry. So those are the symmetries. If I can do two rotations along the axis, that's a symmetry of the system. That takes me back to the original one. Okay, so we see there's a very important point right here in this molecule that brings me back if I go in this direction. So if I go in this direction, right, like this, it brings me back to itself. So there's a rotation through this plane. And that's a 180 rotation takes me back to itself, a pi rotation. So this molecule has this point right here that you can do that through, and that makes it a centrosymmetric molecule. That's just a big word, centrosymmetric. If it was a crystal, so if we have a crystal like this one right here, we could grab a point somewhere, rotate it by 180 degree, and see if we get back the same crystal. And for this one, if we put the center right here and my rotation is along this axis, right, the center right in the center of this, we see that it has that inversion symmetry. And it's centrosymmetric, and the centrosymmetry is right there in the center of this guy. So that's for this cubic cell. So I brought this ones too. This is a little bit different than the centrosymmetric. And then this one, you can tell that this is almost hexagonal, right? So you can see them and play with them. Touch them, rotate them around, see if you can see the planes on it, the facets that it has. Any idea what this makes? No? So this is zinc oxide. So if you work for McElroy, he grows zinc oxide nano springs, right? This is the zinc oxide structure. So zinc, oxygen, oxygen, zinc, oxygen, like that. And this is the zinc oxide, the one that zinc oxide takes. Questions? So you could look at this one and tell me, is there a centrosymmetric point? I mean, with these lattices, right, it's hard to tell because I could try to look, is this rotation through this point right through the center, right? If I do the rotation by 180, do I get back the same thing? But that's basically, it's easier to do with this than, or if you write a computer program to move them around or whatever you want to do, rotations like that. All right, if you have a crystal that is not centrosymmetric, then those are pretty interesting too. Most crystals are centrosymmetric. But if you have one that is not, here's the thing. If we look at a crystal like this guy's, assume that this is cubic or whatever you want it to be, but it's that these are the lattice points on it. If we take that the gold ones are the lattice points, or if we take that all of them are lattice points to make it cubic, all of the points in the lattice are centrosymmetric. Does that make sense? So that makes most cubic, almost all compounds be centrosymmetric. But there's a few that are not. And it would be because one of the atoms is laying farther up or down. So when you rotate it, it's not going to be centrosymmetric again. If you have that displacement that is up or down from where it likes to be, then you have a non-centrosymmetric crystal. And those have really good properties because some of them have ferroelectric properties, for instance. So if you work with Jost or Myers, they have some of those non-centrosymmetric crystals that they're interested in. So I don't know if that's something you're doing. No? You heard about them? No? Okay, so that's something that they like to have. So if you have a crystal and it has some of the symmetries, right? Reflection, rotation, inversion, combinations of them, you can classify them. And the full classification is very technical, but basically there's like 230 something groups that you can classify your crystal into. You discover a new material. You grow something new, a new crystal. Once you grow it, you take it, do X-ray diffraction, or some other means to figure out what is the structure of the system. Once you have this new structure, the program or the crystallographer, if somebody's doing it for you, is going to tell you, this is a blah, blah, blah crystal, and it belongs to a space group, and it's going to give you a number between 1 and 231. And that explains exactly the symmetries of the system. These are all worked out. The only issue for me is that this full classification is very technical. I'm not going to delve into that. I mean, that's a lot of work to go through. But each of this operation tells you, if you can do this operation and go back to yourself, or this combination is what puts you in each of the groups. Does that make sense? So now if you're a crystal grower, like Myers is in his group, then, or Jost when he makes new crystals, they're gonna probably care more about this, guys, and what symmetries you can do. And there's a whole course on doing this. It's called group theory. If you take group theory, they're going to show you how to put this into matrices so that you can look at the rotation and see where the points come back to itself and things like that. Now, if you take group theory from a particle physicist, it's not the same thing, but it's the same math. So it's not going to cover crystals and space groups in group theory for high energy physics, but you're going to be seeing the same math. So those are things that you would cover in those kind of courses. Questions?
Will we be using any methods to carry for the purposes of of this course?
No, you're not, because like I said, it's complicated. I don't want to get into it, but you might need it for your research. Not everybody does, though. And the way I see it is that you can look it up. Once you get a system, you look it up and you can see it on the computer and you can move it around, play with it, make a 3D print of it, and figure out what kind of symmetries you have. All right. The thing, though, is that I'm going to ask you in your next homework to look at rotations, at inversions, and figure it out for some molecules that you're going to make, kind of like this one, or crystals. Okay?
Question. So inversion needs to be done by like needs to have a rotation by like 180 degrees.
Yep.
Always.
Yep. So let me put this by pi 180 degrees. Yeah, a pi or 180 rotation. That's what you want to do.
Kind of, what kind of symmetry
Yeah. So for instance, if you don't have a 180 degrees, but you see that if you do 180 degrees in this direction and then you do another 180 degrees in this direction, you go back to yourself, then that's a symmetry. All right. All right. So lattice and symmetries, that's what I wanted to cover. And now we get into a little bit more complicated things. So this one needs math. That's why I think it's more complicated. So let's talk about reciprocal lattices. Before we said that, oh, one of the symmetries that I didn't talk about is translation symmetry, but that one is obvious, right? If you have a crystal, you look at this point, if you translate it by this distance, from here to here, you get the same thing, that's a translation symmetry. So that's the most obvious one. All right, so if you have a crystal, so if we have a, let's say that we were talking about an electron density in a crystal. So this is given to you by some rho, and it has position like this. And if it's in a crystal, you know that it has this translation symmetry where there's some vector little n right here that you can be moving back and forth and you will get back to itself, right? So that's what the electron density on the crystal is. And this little guy, n, is the lattice vectors that we were talking about. So that Rn is that displacement that takes you back to another lattice point. So any questions about this? No? All right, so one of the things that we do when talking about crystals that are periodic, or in anything that is periodic, is that we want to do a Fourier series expansion of these guys. Because it has this periodicity, you can do the Fourier series expansion of this lattice spacing that we have. So we have a function of the lattice vectors positions. We can then rewrite this function in terms of Fourier series expansions. So to do that makes it useful because of the periodicity translation symmetry of the lattice. So for an arbitrary function like this one, the electron density, we can rewrite it and just make it whatever this R vector is just a summation over N1, N2, and N3 of some function that depends on R. And then we have the N1, A1, N2, A2, N3, A3. So this N1, N2, and N3 are those little lattice vectors that we have up there, right? So this is for this periodic system. We now know that it's going to be periodic and it has whatever N1, N2, and N3 values we want. Remember, N1, N2, and N3 are integers, and this sum would go over all the integers. So we can rewrite this expression as a Fourier series and how many of you don't know what a Fourier series is? You vaguely know? All right. So what we want to do is that this sum is over these integers. We're going to replace it over a set of vectors that go here. And now we have an expression that is like this. So we have a new monster here, these G vectors. And this G vectors is a set of vectors with the periodicity of the lattice. What we're doing here is a Fourier transform. So let me give you an example of a Fourier transform. So let's say we had a function that looks like this. Let's say it's a function of time. So this is f of t. So you take maybe you're doing this in the lab, you're taking measurements, you have it that as a function of time, your measurement oscillates back and forth like this, right? All right, so this is a bunch of data points that you took. What could you analyze out of this? Maybe you look at it and you say like, okay, this goes with a period of something. You could tell what the period is. Cosmo, are you in class? What's the period of this?
Would be some period of 2.
So we could say that it goes from here to here, right? It has a particular period. And along with that, we could also say, if we know what these units are, what is the frequency of these oscillations? Did the Fourier transform of your data, so this could be the sine of omega t, like that. Omega 0. And if you did the Fourier transform of your data, what you would get is that maybe it looks like this, where this is omega 0. So it took you from the time domain to the frequency domain. So this figure right here, that one right there would be this function of omega. And now, if you want to reproduce this signal, you know at what frequency you have to set up your system, and you can get it in time domain. So it's taking you from the time domain to the frequency domain. Make sense? All right, so then if I have another system, and now let's say that this is another function that you have, and it actually looks like this, right? You go and do the Fourier transform of it, and you see that there's two periodicities on it. And it's gonna look like this. Why? Because there's two functions right here, one times the other. So there's a long wavelength, which is the lower frequency. And then there's another frequency inside of this that is going faster. So it's a higher frequency. So that's what the Fourier analysis is doing. It's telling you what your function looks, what periodicity it has. In this case, the omega is related to the frequency, right? And it's related to that periodicity that you have up there. You guys remember how to go from the period to the frequency? You did this in your electronics lab, right? No? So if you know what the period is, now you know what is the frequency. Uh-huh. Mm-hmm. So now this one has two frequencies inside of it. So those two frequencies are here. So now what we're talking about is not a time domain function, but a spatial function. And if we do that, we now have in here, imagine that this became position, the t became position, and this periodicity would be reflected in the equivalent of the frequency, but in real space, for real space. So your time is real space. The frequency is now the equivalent of it in this new system. The equivalent is not frequency, but it's actually reciprocal space. And it's where wave vectors live. So just like here, we have a sine of omega t giving you this or this. What we have here is that your function has the real space function, and now you have a g vector that is the reciprocal space. It's the equivalent of the omega in your sine series. Okay? So this g is a set of wave vectors that is determined by the periodicity of the system that you have. Questions? So how do we determine this periodicity? So the periodicity condition of the system is that e to the I g, one of the vectors g's, dotted with this r plus n1 a1 plus n2 a2 plus n3 a3 is equal to I g dotted with r by itself. So this is any point in the lattice, right? And the symmetry is such that if you travel to another point on the lattice, it has to remain the same. So that's basically what we're saying. We're going from this point R to any point in the lattice, and it didn't change this exponential. So that's that. If you can do that, where you go from one point in the lattice to any other point in the lattice, now you have that this is the symmetry of it. Does that make sense? So this is where people get discouraged about condensed matter physics. If this is something that you don't get, you're always going to hate condensed matter physics. So let me know if you're not understanding what it is. It's hard to see. It's more like it has to click. But this is the symmetry, right? You're going from this point R to whatever n1, n2, n3 can be, whatever integers in your lattice. And this whole expression doesn't change. That's what we're saying. So then if you have found what this G is that does this G is the set of wave vectors that have all of the periodicity of your crystal lattice. So since this has to work for all n1, n2, and n3, then that means that your G dotted with any J could be 1, 2, or 3 is going to be equal to 2 pi times some integer. It could even be 0. So here J is equal to J is equal 1, 2, or 3, and MJ, any integer, including 0. So when we do this operation, right, we go G dotted with R plus G dotted by N1, A1, right? If what we're doing is that we're doing an exponential to something related to 2 pi, we just do another circle, right? Another rotation around the circle. So we're gonna do 2 pi rotations at these values. That's what we want the G to be. When you dot G with AJ, it could be either, if it's 0, 2 pi, negative 2 pi, then you're good. And these AJs are the ones that make up the lattice. Yeah? Sorry? All points in your lattice. Yeah. So all of these points in the lattice could be represented up there. But now if we say that this is the cubic lattice, right? From here to this, these are all the same. Then this one is A1 from here to here. This one is A2, and this one is A3. So our G dotted with A1, A2, and A3 We have to find the G's that when it's dotted with A1, A2, and A3 gives us 2 pi or multiples of 2 pi. So if we found those, then we know what G's fulfill that periodicity up there. So this is the hardest part. That G set of G's that works like that. So let's do an example, okay? I'm gonna have this crystal right here. So let's look at this crystal. We have an A1 right here. Let me call this one A1. And let me call, this is supposed to be symmetric, right? So this one right here is A2. So I have my vectors A1 and A2. So this is a rectangular lattice. I have A1 and A2. Questions? No? All right, so let's give numbers to A1 and A2. So let's say that A1 is equal to 5A in the X direction, and A2 is gonna be 2A in the Y direction. Make sense? So this makes it a rectangular lattice, right? So this is my crystal lattice. It's infinite, but it has that periodicity. So how do I figure out what my G vectors are? We have two vectors right here. A1 and A2. So this J goes 1 and 2 only. So is there a way for me to get G dotted, G1 dotted with A1 is equal to 2 pi M1? Let's say like that, right? So let's make this simpler. All right, let me not use G. Let me use B. So G, this set of vectors, there's two of them. There's B1 and B2. Hold on, let me explain it better. All of the vectors in G can be written as linear combinations of B1 and B2. Does that make sense? Linear algebra, right? Does that make sense? Yeah? We're all good? We're all good? All right. So we have that B1 dotted with A1 has to be a multiple of 2 pi. Can I find one vector that is doing that? Let's say that we want this, 2 pi, right? So the question is, what is B1? If I do that, and I do B1 is equal to 2 pi over A, 5A times X hat, would that work? So I have B1 is gonna be 2 pi over 5AX. So basically I just took this one and put it down here, right? So I know that this one works. Okay. So now I'm gonna have another vector, B2, dotted with A2 is also gonna give me 2 pi. So that means that B2 is equal to 2 pi divided by 2A in the Y hat direction. Does that make sense? All right. So what is B1 dotted with A2? Exactly. And then B2 dotted by A1, 0. So now I have my R vectors, right? Is equal to A1, sorry, A1 and A2. So this A1 and A2 are the vectors that I need to describe any point in my lattice. N1, A1 plus N2, A2 takes me to any point in my lattice. Then I have these G vectors. B1 and B2 that are the reciprocal of this A1 and A2. And I have them here. So I have A1 is 5AX, B1 is 2 pi over 5AX. B2 is 2 pi over 2AY. So those are my two vectors that take me from one point to the other. So again, I have this one. Here is A1. Here is A2. And I can do my Fourier transform on this. And I'm going to get that I have something that looks like this. Does that make sense? And my vector here is B2, and my vector here is B1. So A1 was 5AX, A2 was 2AY, and then B1 was 2 pi over 5x, and B2 is way bigger because B2 is just pi over A in the y direction. So these two vectors give me my lattice points in real space. These two vectors give me this lattice in reciprocal space. B1s, the B2s. If the vectors were cubic, A1 is AX, A2 is AY hat, then these guys would be the same size too, B1 and B2. But because A1 is longer, then B1 is shorter. And if you multiply A1 with B1, you just get 2 pi. You multiply A2 with B2, you also get 2 pi. Questions? We're good? Okay, so with that, that's the end of class for today. We don't have a homework yet. If you have questions about this, just let me know if it's not clear, because the next homework is going to have this: two-dimensional lattices, three-dimensional lattices, finding what is the real space. Sorry, finding what is the reciprocal lattice points for the real space that I give you and things like that. Okay? Yeah. So let me turn this off. One of the